is associated with MCS's rainfall over the Bay of Bengal region. So before going to talk about this thing, I first want to show the percentage contribution of the JJ's rainfall to the annual rainfall over, especially over the Bay of Bengal region. And you can see that the summer rainfall is mostly contributing over the Bay of Bengal region. And there are so many papers which actually shows that it is the large organized convective system, which is popularly known as the mesoscale convective system, that contribute most of its rainfall. In the upcoming slides, I will show, I will prove this statement is correct. So next is I want to show is the, if you calculate the Diurnal cycle of rainfall over this domain, and you plot the phase of the Diurnal cycle of the rainfall over this region, especially, and you will see that, especially if you focus on this Bay of Bengal region, you will see that this open ocean region will have an afternoon maximum of rainfall, which is not typical in other tropical oceans. And this is mainly because you will see that this which is originated in around 2 to 4 GMT. It is actually propagating southward, and there is another phase which is propagating in the eastward direction. So there are papers from our department only, which has explained this southward propagating diurnal MCS and the what is Bay of Bengal region. But there are very least papers which actually explains about this eastward propagating diurnal phase of rainfall over this Bay of Bengal region. So hence I picked up this paper which actually explains this eastward propagating diurnal MCSs over this Bay of Bengal region. So for that, this is the data set they have used rainfall from IMARS, that brightness temperature from this particular data set, and the national parameters from ERA5. So this idea of entire this work is about contribution of MCS's rainfall over this region. So let me first discuss about the methodology they have adopted to identify a system as MCSs and non-MCSs. In the very first, we will pick up the regions which have brightness temperature less than 241 Kelvin, and at least one cold cloud pole which have a brightness temperature less than 225 Kelvin, and they will identify that particular grid as CCS, cold cloud system. Now, if between two successive hourly observations, 50% of the CCS area overlaps between the two successive time intervals, then that CCS is straight. Okay. So now you are identifying the CCS and you are tracking the CCS. Now, if that if you track and if the time or the lifetime of that CCS is greater than 4 hours, and and throughout that lifetime, if the maximum CCS area is greater than at least your 40,000 square kilometer, then they identify that system as an MCS system. Now, if this criteria is met, but either of the two criteria is not met, then they identify their system as non-MCS but as a deep convective system. And if this entire criteria is not met, that means you do not found any cold cloud system over that particular region, then that entire system is classified as shallow or consensus convective system. So if you look at this leftmost panel, this is basically the total rainfall over this region in the year 2001 to 2020 obtained from the IMAX presentation. And you can see that, especially in the morning, that this region and this region is some localized system which is developed. And within the next 18 hours or so, these systems actually merge over this region. So there, whatever phase propagation I have plotted previously is actually, if you also plot the hourly rainfall hour by hour, you'll also see such propagations which are present there. Now, if you classify those or if you segregate those total rainfall into two parts as MCSS and non-MCSS system, you could see that this MCSS is mostly contributing to this propagation in compared to the non-MCSS system. So they basically focus here only on those MCSS systems which are contributing to this propagation, and there are two types of propagation, southward and eastward. They are only focusing on those MCSS signals which are propagating eastward. Eastward. Yeah. From here, this system originates and it comes eastward. Yeah. So this is the special plot of the MCS initiation frequency. And if you look at if you look at the Bay of Bengal, this is the east coast of the Bay of Bengal region. This is the west coast of the Bay of Bengal region. Now you can see that the MCS initiation frequency is higher over the east coast of the Bay of Bengal region as compared to the west coast of the Bay of Bengal region. And this is not surprising because this is actually in the downslope portion of the prevailing monsoonal winds, which will carry enormous moisture over this region, and there is always orography and coastal regions present, which will always initiate convection over this region. And one more important point is that if you look at this CS plot here, yes, throughout the entire day you will find this rain band present over this east coast of the Bay of Bengal region, which actually suggests that the maximum of initiation frequency of MCSS in the east coast of the Bay of Bengal region and the maximum of rainfall value of MCSS rainfall value in the east coast of Bay of Bengal region coincide. That means they do not move; they stay there. They initiate there and they stay there. This is because you will always get this flow which will not allow to move the MCSS system this way. Now there are also some, although it is different than the east coast of the Bay of Bengal region, but there are this initiation of MCSS is also found in the west coast of the Bay of Bengal region, and you can see that these systems which are initiated here, these are actually propagating here. So they have drawn a line passing through the maximum initiation frequency over this west coast of the Bay of Bengal region, passing through this line, and throughout this line, in order to confirm that this initiation frequency or the MCSS rainfall are actually propagating or not. So throughout this line, they plotted the homolar diagram first of the MCSS initiation frequency. So from this plot, what we can see is that so this horizontal axis is basically this black line, okay, and this coastline is actually this particular line, okay. So this is the separation between the land and coastal region. So you can see that in the land region, mostly the MCSS initiates over the afternoon region, afternoon time, and in the oceanic region, it initiates in the early morning time. And if you look at the open oceans, which they are identified as greater than 400 kilometers from the coast, in the open oceanic regions, this actually MCSS initiation frequency is actually higher at 00 LST. And but within this 400 kilometers, you see, it initiates here, and you can see a clear propagation within the next 6 hours at a distance of about 400 kilometers from the coastline. That means they propagate at around 19 meters per second. So, and another thing is that the highest MCS initiation frequency, you note this point, the highest initiation frequency is found at around 30 kilometers from the coastline and at almost at around 00 LST. Now, if you look at same thing, if you just look for the precipitation part, you can see that precipitation starting to initiate over the coastline at around morning time, and within the next 18 hours or so, it propagates to about 800 kilometers from the coastline. So, and the second thing is that this speed of propagation, if you can, is much slower than, comparatively slightly slower than that what you found for the MCS initiation frequency. That means initiation frequency of MCSS travels faster than rainfall. And this, the hypothesis is that because initiation frequency is faster, they may be directly related to the diurnal gravity waves which are created. But you cannot link directly to the propagation of precipitation to the diurnal gravity waves, because precipitation along with the diurnal gravity waves, it will also depend on how the cloud systems of MCSS are also moving towards it, which is again dependent on the background flow as well as the cold pool dynamics associated with that. Now, another thing if you notice is that the heavy MCSS area, this is one, it is found at around 400 kilometers from the coastline, and it is popping at around 6 LST. That means the time of initiation of the time when it was formed, it is maximum at around 0 LST, but the time of maximum of rainfall is around 6 LST, and also the distance is farther. That means the time when it is just initiated, the rainfall accumulated is very less. But as the time progresses, because MCS needs systems to what you call collaborate with each other. So as the systems grow, then only you will get the maximum at a later time and at a later place than when it was initiated. Another interesting thing found was that the inland precipitation or the inland MCSS rainfall is less as compared to the open ocean MCSS rainfall, and this is very obvious because this is basically the left hand side of the coastline, which is actually the dry region, because there is the western part of the region which causes the dry intrusion over this region, which will actually inhibit the convection, which will not allow MCSS to bloom. So maybe that because of that reason only, the amount of precipitation associated with MCSS rainfall is less over the inland region as compared to the offshore region.
Why the rainfall going eastward?
Why the rainfall? I will come back because they will. Okay. So now this is the contour lines are basically the wind anomalies, and the dotted lines basically show onshore propagation, and the solid lines show the offshore propagation. And if you focus on the contour lines, you can see that the onshore propagation reaches the coastline in the afternoon hours, and the offshore propagation reaches the coastline in the morning hours. Now, this onshore propagation reaching in the afternoon hours in the coastline, it actually creates these shaded lines are the divergence. The negative value indicates convergence and positive value indicates divergence. So, the onshore propagation reaching the coastline produces convergence in the afternoon time for the land region, and this causes convergence in the open oceanic regions in the morning time. Now, another thing is that this what you call contour lines, they can travel to a much farther distance, to say greater than 800 kilometers. So that means this you cannot identify this as a consequence of local land sea bridge phenomenon, because of the fact that the propagation distance is greater than or 800 kilometers, which is approximately 1000 kilometers, and the propagation speed is about 14 to 19 meter per second, and the horizontal wavelength that you will find out is approximately 600 to 1200 kilometers. So these features is reported in this paper, which shows significant important resemblance with the tropical diurnal gravity waves. So which allows them to hypothesize that there is although local land sea breeze phenomenon associated with it, but the propagation of these perturbations or the onshore propagations or the offshore propagations associated with these gravity waves is not solely because of this localized land sea breeze. This will be connected to. In order to prove this hypothesis, they have designed a 2D linear model solving the 2D equations which we know, and I will not go into the details in the additional slides. If someone wants, I will explain better. So what they found out, they solved in solving that if you have a given Q profile, and if you have a given U and run by a frequency profile, you can calculate all the variables in that equation. So for that, what they have done, the experiment, they have allowed they have allowed the land temperature to vary diagonally, but they have allowed the sea temperature to remain constant, and that means they are diagonally forcing the land, and this is basically the model specifications. And from that, they have done 4 experiments. The first experiment is keeping the horizontal background wind 0, and the n, that is run by frequency, the vertical profile of the at some value which they have got calculated. Okay, so now if you look at this, actually the onshore propagation reaching the coastline in the afternoon hours, and the offshore propagation reaching the coastline in the morning hours are found here also. But the propagation distance is very, very less. It is about 200 kilometers in the 24 hours of interval, which is approximately 2.3 meters per second. So that means this whatever propagation that was traveling greater than 800 kilometers was not because of this particular condition. Now, if you put a realistic N profile, that means if you allow the Brand-Pascal frequency to vary vertically, but again you keep U equal to 0, there's no background flow, you will again get a similar thing. There will be only slight improvement over there, but again the distance of propagation is not too much. So again, that means in order to have a propagation distance of greater than 800 kilometers, you need to have at least some background wind velocity associated with it. So in the next part, they have chosen a velocity of U equal to 5.7, which is basically the average of the surface velocity found over this region. So they have taken a constant u velocity and the earlier realistic end profile. And now it comes similar to what we have seen in the era 5 observation. Era 5 have considered this as observation. They have considered this as observation. That's right. So you can see that they are you can at least found that the propagating distance of this wave are greater than 800 kilometers. The only discrepancy found was that these magnitudes are comparatively higher as compared to the era 5. And other thing is that in era 5, this happens at a later time. That means the convergence time over land or the oceanic region happens at a later time, whereas in linear model, it happens at an earlier time. Now, another discrepancy is that if you look at this onshore propagation, they cannot penetrate into the land. This is because this onshore propagation, they cannot penetrate into the land. This is because there is a constant u velocity you have applied throughout the entire vertical profile. There is a constant u velocity from the land region to the oceanic region, which will prevent this what we call perturbations to reach the land region. Now, the last one they have done with a realistic U profile and a realistic N profile. And now the things are at least still 600 kilometer. If you compare the first 600 kilometer from the coastline, the magnitudes are comparable and the time of occurrence of convergence is comparable. The time of initiation of convergence is also comparable. The only discrepancy found was greater than 600 kilometer. The waves are traveling slower as compared to that it was in the era 5. This is because in era 5, because there were this was pure in era 5, the waves, diurnal gravity waves coming from both the coast, north coast as well as the west coast of the Bay of Bengal merges and moves. That's why their speed was faster. But here they were only considering this eastward propagating coming from the west coast of the Bay of Bengal region, and because of that, this speed is slower. Another discrepancy found was that this part, if you look at in the era 5 observation, yeah, so this part you will not find too much of things happening here. This is because there is no orography here. So because of the less amount of orography, because of no orography, this feature is still present, which is again a discrepancy in the models. But they were just trying to explain the propagation of these rainfall bands are associated with the diurnal gravity of gravity waves or not, and at least for 600 kilometers they could explain, because of which they finally drew this conclusion that there was a clear diurnal propagation of rainfall from Bay of Bengal to west coast of Bay of Bengal to the central Bay of Bengal region, which is mostly driven by the propagation of the MCS precipitation. Now, besides MCS rainfall, MCS initiation frequency is also propagating in the offshore direction, but it is at a faster rate as compared to that over the MCS rainfall. Now, these gravity waves which are triggered by land-sea thermal contrast, they are they are essential for only the creation of the what you call wind perturbations or the wind anomalies near the shore. But the propagation, it actually not only depends on the diurnal gravity waves triggered by the land-sea thermal contrast, they are also dependent on the background profiles of the wind. So both mean wind speed and the vertical wind shear are actually important in this offshore propagating waves. That's all.
Next question. How about the role of Eastern Ghats, the orography there? Does it affect this?
That part they have not. I mean, they have not put any orography, so then they could not explain from that linear. But most importantly, they were looking at only this part, I mean, oceanic part. So, like Stangan will have anything.
Yeah. But the same thing will happen on the East Asian coast to West Pacific?
Yes.
Same thing?
Or maybe.
Interesting. Level cycle is it only because of Bay of Bengal or West Pacific also a similar feature?
Might be.
Okay. Yeah.
But actually prescribed the Q profile, the heating profile. They have prescribed a heating profile, right?
Yes. This is basically the black line that they have done. They have done one more thing, importance of background wind, because of which they have classified into weak monsoon. This I'm not going to discuss. Only focus on the black average line. This is the Brand-Weissler frequency profile, which is the realistic N profile, which I was talking about. And this is the black line is basically the realistic U profile. And regarding the Q value, this is the Q profile. on is the maximum heating, okay, and this Ux is the vertical, horizontal distribution of the heating rate, and this Vz is the vertical distribution of the heating rate, and this Q0 they have taken as this is the value which we have taken from CR paper. Vz they have taken as this one, and this H value have taken this one. So from that they have calculated this part. So this is basically the horizontal distribution along this part. Yes.
The NCA do not last very long, right? How long do they last? NCA. Maybe 2 hours, couple of hours or so. Isn't it? The time scale is much larger.
Yeah.
But I'm asking that do they differentiate between games, propagation of NCA generation location and with the NCA propagation direction?
They have seen the MCSS any initiation, propagation of initiation of MCSS, but they have not looked at that other part, lifetime, what you're talking about.
Yeah, so the direction model, that's what I'm asking. So the initiation is equivalent to rainfall or existence, the NCA or not. That's what my
Yes.
question is.
Okay. That part I think it's not mentioned.
The classification that's it's
Which one?
lifetime mentions.
It's greater than 4 hours. That thing is mentioned that if any system has greater than 4 hours, then only they will consider this as MCS. That part is only they have discussed. But regarding how much duration total, that they have not covered that part. Only a minimum criteria only they have.
And if you go north of 20 north, will there be other way around?
It might be.
Going like can be enough for a cold deep convective system, I guess.
This they have taken from Chain et al. 2017 something that paper this criteria they have described their part. So if they've used their maybe this not that well enough, but at least you can identify the MCSS system on an average. Because this
And what was the level of the divergence surface or above the boundary?
which this divergence plot each surface low level convergence surface divergence plot.
I wondered if you have taken anything above the boundary there was one, and they should have checked it. I think they would have got, I think, some benefits and effects. And I think 225 Kelvin is not that it's one. They should have taken a golden threshold lights from being.
Yeah, but there are two criteria. Right? First of all, that is for the only for the cold core, but then again, the surrounding regions or at least in the particular green point, they mentioned two criteria. So I think that enough for if you do a longer research. But if you just want to track a particular system, then that value will change because this is on an average picture of around 20 years. So that will go up.
Very good.
Thank you. Very much. Yeah. So the monsoon is going along very smoothly, and so we are plus 15% in all of this, and right now, till yesterday, plus 40% in September, and both IMD and SkyMet have said that rainfall in September will be 10% above normal, 9 to 10% direction, and of course, for the whole period, they're already 8% above normal. So it will come close to the forecast made by most of these things. Now, if you look at the core monsoon zone, till today, I don't know why they update this very quickly, but rest of the thing they don't update. So till today, it's going extremely well, well above the normal, and there are no indications that this is going to die down. Now, the surprise part is, Robert, we are still not gone to La Nina. You can see the neutral phase. And so the question is, why this thing is doing so well without any external effects? Now, just last week, you saw two depressions. One, this one, which called bottom green here, this one was Gujarat. And so some of these are still continuing. There was a rainfall, and it was a big floods in Gujarat last 2 days. Now, I was wondering how good the forecast was. This is their verification. This is for last week, 25th August. Okay, this heavy rainfall has occurred. So 1 day forecast is very good. I would say 2 days is not bad. Third is sort of okay. Fourth, already it is confined only to the Konkan coast here, not to the whole region. But this is not so good, showing rain where they never occurred. So this shows that as of now, heavy rainfall events, IMD's forecast is reliable the first 3 days, I would say. After that, it starts falling apart. So to me, I find this is much more useful than correlations and all these various metrics. They average over everything, and you don't get a good picture. So look at actual one event, you can see that it's not easy to predict a very heavy rainfall stuff. Now let's look at something peculiar about this year, which is not discussed by anyone, which is this feature. Arinam says it's part of PDO, probably it is, because outside the tropics. And according to NASA website, sorry, NOAA website, it is 4.5 degrees above normal. Okay, I can't believe it. I've never seen that kind of anomaly, but remember, we all are used to tropics. In tropics, things cannot go too far high. For example, here it's still at the most you get 2 degrees. So this is 4.5 degrees above normal. And it was quite large domain, not small. So I've not seen a single paper. There are a few papers. I think Sulochana published paper about the June rainfall, right? There's one. But this is there in June, July, August, September. It is sitting there. Nobody explained why it is so high, why there's such a big block, and what is it doing to monsoon. I have not seen any paper. If you have seen it, to tell me. Okay. Now, what it is doing is very interesting. I just plotted the geopotential height at 200 millibars. Because that shows you the column mean temperature. That's what we want. And it is clearly affecting that. You can see that. Okay? So that warm patch of ocean around 45 north is causing that column to warm up and surely an effect. And it should affect the propagation of waves along the direction. Definitely, right? So we will see that next. So this is the rainfall anomaly for the whole period, June to August, and as expected, pretty except that I'm surprised by this. It's saying 4 millimeters per day above normal. Can't believe it, because our mean rainfall is 7 millimeters per day, 50% above normal. I'm a bit surprised. Maybe there are problems with this data. This is from the NOAA website, and you also see typically. Similar thing happened over Indonesia. Okay. But in between, you have this negative anomaly here and here. So it's a very local feature and local feature here. In between, all kinds of things happening here. And so I looked at the velocity potential just to see what's happening at the upper level. And yes, upper level, in the month of July, the upper level divergence, which would have helped. And there is a clear diverse structure here. And what I'm surprised by is this is happening during El Nino year is La Nina year is not surprising. But there's no La Nina. Still there's a diverse structure. Okay? Something else is triggering it. I don't know what it is. This is July. And this is August. And what it does, it is shifted towards India. Okay? Still we have diverse structure, but it is shifted to the west here. And that may have partly contributed to high rainfall in India. Okay. Then you see what happened in June. Okay. In June also, it is here over Indonesia, not over Australia. Yeah, of course. In June we had a monsoon somewhat delayed and went up. So you can see the level convergence. Okay. Something happened in June and July, it shifted the whole thing. Okay, now if you look at the big picture of the rainfall anomaly from August alone, August was unusual. Again, same structure, Indonesia, India, and this region where there was a warm ocean. This is showing its effect here right here. Nothing over this region because it's close the neutral. And if you look at the meridional bend to look at Rossby wave, you see, yes, this is having some effect. Not substantial, but that's a very large anomaly. This is for the month of July, okay? And if you see August, it's even better. Much more clearly defined. I would say one can see the Rossby wave all the way like that. So the question is, did it play some role over in there? One has to see whether one can connect that shift in the Rossby wave to the rainfall of India. Okay. Now, this is a column water vapor, always my favorite. And what amazes me, I don't know how good this ANSWER data is 20 kg per meter square of this region. Okay. Just those few depressions over Gujarat and Pakistan created so much anomaly in the month of August. Okay? And it's much higher than what is in Indonesia. And this is month of whole period. I just to the entire period also. That anomaly is seen clearly. And yeah, this goes along with these 3 points are all with rainfall. No surprise. All the three are related to rainfall picture. Okay, let's remind you that almost all models are predicting above normal rainfall right here, which is happening at present, and below normal here, which all of us are aware of, and of course, below normal here, just to be expected with the shift of the system. Okay. Now let me go back to what happened this year, looking at Arindam's work. So Arindam is looking at transition from El Nino to La Nina, El Nino to neutral, El Nino to El Nino. If you just look at data, the most probable thing that will happen after El Nino is neutral. There are 23 or 24, there is only about 9 or so. Okay? So we are going toward neutral mostly because that's the most probable one. And there's only 3 plus 3, only 9 in this. And it's even less, 3 plus 4, 7. So this is the most probable transition, El Nino to neutral, not surprising. Okay, now if you look at this picture, everybody was expecting this. So with great confidence, they said 99.8%, the 10% more normal. They'll come out right. But the fact is, with a neutral situation, we should be here. Here, I think the confidence level is very low. Am I right? You are saying you're not confident that we're above normal. Am I right? So that bothers me. I looked at the actual data. You tell me, because if you look at all these years in your supplementary material, okay, most of these things are normal or above normal. Okay, I don't know why you get such a so low value.
Standard deviation is large.
Huh?
Standard deviation is large.
Okay, it's very large. Okay, but come on, when I look at actual data here, there are not too many drought cases, very few. Okay, maybe 2 or 3 at numbers. About 15 are normal, 4 above normal, and 1 or 2 normal. So I would have thought that you would have got a lower value. So that contrast between 99.7 and 20 sort of bothers me. You tell me what explanation for that is. The one thing interesting there I found is what you also made a prediction regionally, and this one you're going to get right. So this year, the Peninsular India is going to be well above normal. So your confidence level there comes out right. But we have to see, rest of the thing we'll see. All of them come out right or not. Other thing Arindam has done is to plot the rainfall distribution when there's a winter La Nina or winter El Nino. So we had a winter El Nino last winter, right? So the only difference is the distribution is very similar. The difference is this. Okay? From plus being the highest probability. You here that's highest probability, but the percentage goes down. Okay? But I'm really surprised because whether you come from a winter El Nino or La Nina, the shape is almost same. So I don't know what it is telling us. I'm a bit surprised. I expected much bigger difference. Okay, so I'll add with the paper I saw recently in Advanced Atmospheric Science, trying to predict how the boreal summer interest oscillation will change under global warming using CMX model. Okay. Now, point is out because for the last 20 years, I've seen so into population and climate change. Most of them. Okay. Now, why is that? I have a point with the IPC data, they quite on this issue. The point about this, these CMX models look at their present historical simulation with what is observed. Okay. These are the various phases. Think of the MGO phase. They are not getting the right maximum. Okay. And you are and the difference between future and historical is very little. Okay. So to me, it has no sense. It is junk. Okay. The same thing is happening with regard to global warming. All the document IPCC puts out, people talk about CMX and so many what will happen in the future, but those models cannot simulate mountain correction. So why look at the future? So I argue that IPCC don't put it up because the difference between the model simulation, historical simulation, and observation is larger than double CO2 and the models presently having. So there's nothing in it. So I said, don't put it there, there is actually because there are other political go. I said, this you're putting out, people are going to believe that it has no value because the model cannot get the present climate correctly. There is no point in talking about the future. Otherwise, any number of people I've seen in the last 10, 20 years, or impact of aerosol or monsoon or something, their monsoon is not right in the present climate. And as you know, most models have a dry bias like CFSV2. So we really cannot use that model to say what will happen in the future. Okay. So this to me is a slight example that we're not able to get the distribution of the interseasonal modes and your population we were saying, then of course there's a nice statement they have made. There's no broad agreement among the models. Okay. But they are making claims about how from this what will happen in the future. I don't think we can tell, but the point is that the models that at this stage are not good enough to tell us what will happen in the future, either interseasonal or seasonal or even longer scale or even linear. In all of them, the models are failing badly. Now, you don't want to say this in public because you won't get funding. Okay, this is a problem all over the world. So you have to pretend your model is doing well because you tell the truth. Don't get credit. But there's a fact. I think it's good to admit that problem is tough. It's going to take some more time, more observation, higher resolution model in order to capture all the features. So we'll keep trying, but we will not promise that we'll give you a product which will actually help you to with the future. This is the problem I face, and many of the NGOs don't understand it. NGOs are putting out all kinds of nice products saying, I'll tell you what will happen next decade in Bangalore or in Gulbarga or Vijayapur. I mean, it's nonsense. I mean, models cannot simulate on that scale. We know that. Okay. But the NGOs who read all these reports, they don't know that. They put out nice color pictures, and our great politicians are making policies based on that. Okay? And none of the models can any other present day future correctly, especially spatial structure. Okay. Which is very tough, we know that. Okay. If you don't get that right, how can you say what will happen in Bangalore 10 years from now? You cannot. But there are whole sort of climate change reports for every state in India put out by NGOs who made some money out of that. So that's a fact about this kind of work. So be aware of that. Okay. Okay. So next week it is Chetan, right? Okay. Thanks. Any questions? Anybody here? Online?
I have a question. What is that case 4 and 5? 4 and 5 is
No, I didn't follow. What did you say?
that 4 and 5 phase
Yeah.
responds to what location of the item?
Yeah. This one they're doing very bad. Yeah. But even this one, look at this. I mean, I would generally say the observation is saying that this is where most of the time the model is not getting that. Right?
Yeah.
So that's the point. So what's the point in talking about future if we don't get the present correctly? Okay.